Hello everyone. Today I will start about this chapter of the alcohol, phenol and ether to discuss about it in very detail. First one example is the monohydric alcohol, second one is dihydric alcohol, third one is trihydric alcohol. First one name is ethanol, second one is name is ethylene 1,2-diol and third one is glycerol. Next, classification of alcohol as primary, secondary and tertiary. If there is one alkyl group, so it is primary. If two alkyl group present, then it is secondary, and if there is present three alkyl group with the carbon attaching with the OH, it will give tertiary alcohol. The seventh example, also a primary alcohol. Next is secondary alcohol. This is tertiary alcohol. It is also primary alcohol, it is also secondary alcohol, it is also tertiary alcohol. And now come to the monohydric phenol. First one is phenol, second one is monohydric and cresol, its name is cresol, and second one is, third one is catechol, and fourth one is benzene 1,2,4. Triol, benzene 1,2,4 triol. Common and equate name of some alcohol. First one is methyl alcohol or methanol, second one is N-propyl alcohol or N-propanol. Third one is isopropyl alcohol. Third one is isopropyl alcohol or propan-2-ol. Fourth one is N-butyl alcohol or butanol. Fifth one is sec-butyl alcohol or butan-2-ol. Next one is isobutyl alcohol or 2-methyl propan-1-ol. Next is tert-butyl alcohol, 2-methyl propan-2-ol. Next one is ethylene glycol or ethane 1,2-diol, and the last one is glycerol. Its name is propane 1,2,3-triol. Cyclic alcohols are named using the prefix cyclo, considering the OH group and attaching to the C1 carbon. So first one is here cyclohexanol, second one is here 2-methyl cyclopentanol. Common name and equate name. First one is phenol, second one is orthocresol or 2-methyl phenol, third one is metacresol, next is paracresol. This is catechol, ortho-dihydroxyphenol, ortho-dihydroxybenzene or benzene 1,2-diol. Third one is resorcinol or benzene 1,3-diol. Fourth one is hydroquinone or quinol, benzene 1,4-diol. Common names of ethers derivative: dimethyl ether, diethyl ether, methyl N-propyl ether. Next one is methyl phenyl ether or anisole. Methyl phenyl ether or phenolate. Methyl isopropyl ether, 2-methoxypropane. Phenyl isopentyl ether, phenyl isopentyl ether or 3-methyl butoxybenzene. Next one is 1,2-dimethoxyethane. The last one is 2-ethoxy 1,1-dimethyl cyclohexane. Here are these some structures of the alcohol, such as methanol, phenol, methoxy, methane. The bond angle is 109 degree 28 minute around. For methanol it is 108.9 degree due to the presence of two lone pair, and here for phenol it is 109 degree, and for ether it is 111 degree. The bond angle in alcohol is slightly less than the tetrahedral angle. It is due to the repulsion between the unshared pair of the oxygen atom. In phenols, the OH group is attached to sp2 hybridized. OH group is attached to sp2 hybridized carbon atom of the aromatic ring. The carbon oxygen bond length 136 picometer in phenol is slightly less than that of methanol, where the bond length is 142 picometer. Here the CO bond length is 136 picometer. This is due to partial double bond character on account of the conjugation of the unshared electron pair of oxygen with aromatic ring. Second is sp2 hybridized state of the carbon to which oxygen is attached. Preparation of alcohol. Preparation of alcohol from alkenes by hydration in presence of acid catalyzed in presence of acid, or it is called acid catalyzed hydration reaction. So ethene bond will be converted into alcoholic bond. It will follow the Markovnikov rule of addition reaction. So propylene under such reaction will be converted into prop-2-ol or propane-2-ol. Here is the mechanism given. First, the proton is captured by the pi electron cloud, then the generation of the carbocation, stable carbocation, and next step is the donation from water to form an alcohol. Next reaction, preparation by hydroboration and oxidation. First, hydroboration reaction will be done with the alkene. So this will follow the Markovnikov addition also. Which will be converted into trialkyl boron, and then trialkyl boron is, when oxidized with peroxide in presence of OH minus or basic medium, it will be converted into primary alcohol propan-1-ol from carbonyl compound by reduction. If we reduce the aldehyde group with H2 palladium, it will be converted into primary alcohol, and ketone with lithium aluminum hydride or sodium borohydride, it will be converted into secondary alcohol. And carboxylic acid, if we reduce with lithium aluminum hydride or water and give water, it will be converted into primary alcohol. And carboxylic acid, if converted into first ester, then ester is reduced with hydrogen and catalyst, then also it will be converted into primary alcohol with cleavage of the bond, with cleavage of the ester bond. Now from Grignard reagent. The Grignard reagent RMGX, when tries to react with carbonyl compound, it will give a tertiary alcohol. This. The formaldehyde will give primary alcohol, and if there presents R group, it will give a, here one group is present here, it will give a secondary alcohol, and if ketone group is present, it will give a tertiary alcohol. Now come to preparation of phenols. Phenols can be prepared from haloarenes by the substitution reaction under harsh condition like 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of the sodium phenoxide to produce phenol. So chlorobenzene in presence of NaOH is converted into phenoxide ion. Then if acid is given, then this phenoxide ion will be converted into phenol. Second, from benzene sulfonic acid. When the benzene is treated with oleum, it will be converted into benzene sulfonic acid. It will be converted into benzene sulfonic acid, and benzene sulfonic acid, when treated with NaOH first and then H+, it will be converted into phenol from diazonium salt. If primary aromatic amine such as aniline is treated with NaNO2HCl in presence of ice or 0 to 5 degree centigrade temperature, this will be converted into first benzene diazonium salt, and then benzene diazonium salt, if warmed with water, then it will be converted into phenol with the liberation of the nitrogen. From cumene phenol. When cumene is oxidized in presence of oxygen, it forms cumene peroxide as an intermediate. Then cumene peroxide will be converted into phenol with a rearrangement reaction, and acetone will be a byproduct. Physical properties. Alcohol phenols consist of two parts, alkyl or aryl group and a hydroxyl group. The properties of alcohol and phenol are chiefly due to the hydroxyl group. The nature of the alkyl and aryl groups are simply modify these properties. Boiling points. The boiling points of the alcohol and phenol increases with increasing the number of the carbon atoms. That is, the increase of van der Waals forces. In alcohol, the boiling point decreases with increasing the branching in the carbon chain because of the decrease in the van der Waals forces and the decrease in the surface area. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding. So due to this intermolecular hydrogen bonding, the boiling point of alcohol and phenols are slightly higher than ether or alkane compound. It is interesting to note that the boiling point of the alcohol and phenol are higher in comparison to the other classes of the compound, namely hydrocarbons, ethers, haloalkanes, haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but the boiling point differs widely. The boiling point mainly boiling point of methoxymethane is intermediate of two boiling points. Here is some example of ethanol, methoxymethane and propane. Their molecular weights are more or less comparable. Ethanol has highest boiling point than ether. Then ether has highest boiling point than propane. The high boiling point of alcohol are mainly due to the presence of intermolecular hydrogen bonding in them. Solubility of the alcohol and phenols in water is due to the ability to form hydrogen bonds with other water molecules as shown. The solubility decreases with increasing the size of the alkyl or aryl groups. The several of lower molecular masses of alcohol are miscible with the water in all proportions. Chemical reactions. When alcohol acts as a nucleophile and attacks the carbocation, it forms ether. When alcoholic OH group is protonated with hydracids like HBr, the OH group will be expelled as water and bromine will attack the carbocation to form a bromobenzene here. Reaction involving the OH bond. So OH bond is actually active bond. So OH bond is slightly acidic here. It will react with sodium metal to give hydrogen and it will form a sodium alkoxide. With aluminium it will form aluminium tert butoxide here or aluminium alkoxide with the release of the hydrogen. This is the proof that here OH group is polar, there is a presence of OH group. Now come to phenol. Phenol also reacts with sodium to give sodium phenoxide with the release of hydrogen, and sodium and phenol with the reaction of NaOH also give sodium phenoxide with the release of water. Acidity of the alcohol. Primary alcohol has higher acidity than secondary alcohol, than tertiary alcohol. It is due to the Classe and Placer effect. Alcohols are weaker acid. Its conjugate base. Alcohols are weaker acid, so its conjugate base is stronger. That is, alkoxide is a stronger base. Acidity of phenol. Acidity of phenol can be explained due to the resonance structure of the phenol, and the resonance structures of phenol shows that there creates a positive charge on the oxygen atom, and which exerts a force to release the OH bond easily to attain the stability of the stability of its conjugate base. Its conjugate base phenoxide ion has lower energy, so it is stabilized, highly stabilized due to its resonating structures like 1, 2, 3, 4, 5. These are 5 resonating structures of the phenoxide ion, and due to the stability of this phenoxide ion, phenol acts as a strong acid, then also carboxylic acid. In substituted phenol, the presence of the electronegatoring group such as nitro group enhances the acidic strength of the phenol. This effect more pronounced when such group is present at ortho and para position. It is due to the effective delocalization of the negative charge in phenoxide ion. When the substituent is at ortho and para position, on the other hand, the electron releasing groups such as alkyl group in general do not favor the formation of the phenoxide ion, resulting in the decrease in the acid strength. Cresol, for example, are less acidic than phenol. Orthonitrophenol. pKa value is 7.2. Metanitrophenol, pKa value is 8.3. Paranitrophenol 7.1. So here paranitrophenol has highest acidity. As pKa value is lesser, it suggests that paranitrophenol is more acidic than the orthonitrophenol. Orthocresol has pKa value 10.2. is suggesting that one methyl group It's suggesting that one methyl group exerting the plus I effect and reducing the acidic character of this phenol. Metacrozole has also similar 10.1, paracrozole also 10.2, and ethanol has 15.9. Here is for ethanol no such stabilization factor. Now come to esterification. Alcohol and phenol reacts with the carboxylic acid to give an ester compound in presence of acid. So esterification is always acid catalyzed. Reaction involving cleavage of the carbon oxygen bond. The reaction involving cleavage of the carbon oxygen bond takes place only in the alcohols. Phenols show this type of reaction only with zinc. So reaction with hydracids, ROH, give RX. So alcohols can be detected with Lucas test. The Lucas reagent is concentrated HCl and ZnCl2, and in this Lucas reagent test, when the Lucas reagent is added to the tertiary alcohol, the turbidity appears immediately for tertiary alcohol. For secondary alcohol it takes 3 to 5 minutes, and for primary alcohol it takes several hours. By this we can determine which one is primary alcohol, which one is secondary alcohol, which one is tertiary alcohol. The reaction with phosphorus trihalide. Alcohols are converted to alkyl bromide by the reaction with the phosphorus tribromide. Dehydration. Alcohol undergo dehydration in presence of concentrated sulfuric acid or phosphoric acid, or catalyst such as anhydrous zinc, anhydrous ZnCl2 or alumina. This HOH will be out and alkene will be formed. Ethanol undergoes dehydration reaction by heating with the concentrated H2SO4. It will give alkene as a product. Here the secondary alcohol proptol, when treated with 85% H3PO4, it will give an alkene, propene, and it is tart butyl alcohol. When given 20% H3PO4, it will give 20% H3PO4 358 Kelvin. It will give it will give 2-methyl propene. The relative age of dehydration. The relative age of dehydration of the alcohols are as follows: tertiary greater than secondary greater than primary. It is the mechanism. At first protonated alcohol is formed, and from this protonated alcohol dehydration occurs and the formation of the stable carbocation occurs, and then from stable carbocation release of one hydrogen, release of one proton generates the alkene. So more substituted alkene will be the major product. Oxidation. Oxidation of alcohol can be converted into carbonyl compound such as the aldehyde and ketone. Further oxidation can oxidize it into carboxylic acid. This. So if we give chromium trioxide, it will produce, primary alcohol will produce aldehyde. If we give PCC, this double bond will not be oxidized and the alcohol will be oxidized to aldehyde. If the secondary alcohol is oxidized with CrO3, it will be converted into ketone. The tertiary alcohol do not undergo oxidation reaction. Under strong reaction conditions such as strong oxidizing agent KMnO4 and elevated temperature cleavage of the various CC bond take place and mixture of the carboxylic acid containing lesser number of the carbon atom is formed. RCH2H Cu RCHO oxidation with the copper. So this will be ketone and this will be an alkene. RCH2H converted into copper, converted into aldehyde in presence of copper, 573 Kelvin temperature. For tertiary alcohol, it is not oxidized, it is dehydrogenated. To form alkene. Not dehydrogenation, it is dehydration. It is dehydration to form alkene compound for tertiary alcohol. Now come to electrophilic aromatic substitution. For phenol, here dilute HNO3 will give orthonitrophenol and para-nitrophenol. So para will be the major product. Here we do not use concentrated HNO3. Concentrated HNO3 will break the pi bonds of the benzene ring and it will form a quinone as a compound. It will oxidize the ring. So we use dilute HNO3 for nitration of the phenolic compound. So orthonitrophenol here has intramolecular hydrogen bonding, and here para-nitrophenol has intermolecular hydrogen bonding. So due to this intermolecular hydrogen bonding, para-nitrophenol has higher boiling point, melting point, but orthonitrophenol has lower melting point, or it is considered as volatile substance. With concentrated nitric acid, phenol is converted into 2,4,6 trinitrophenol. The product is commonly known as the picric acid. Nowadays, picric acid is prepared by treating phenol first with the concentrated sulfuric acid, then which converts it to phenol to 2,4-disulfonic acid, and then concentrated nitric acid to get 2,4,6 trinitrophenol. Now halogenation reaction. If we treat bromine in presence of CH2 or acetic acid, it will form para-bromo product as major and ortho-bromo as minor. But if we give bromine in water in phenolic compound, so it will give a tri-bromo product as a peculiar product. Bromine water will produce tri-bromo phenol as 2,4,6 tri-bromo phenol as peculiar product. Kolbe's reaction. Kolbe's reaction. First, phenol is converted into phenoxide ion with NaOH. Then, carbon dioxide is passed through it. So, carbon dioxide will be added into the ortho position, and 2-hydroxybenzoic acid or salicylic acid will be the major product. This is Kolbe's reaction. Now come to important reaction, Reimer-Tiemann reaction. The reagent is chloroform in aqueous NaOH. Chloroform in aqueous NaOH will form a carbene, and this carbene will react with phenoxide ion and it will be converted into salicyldehyde as a final product. Reaction with phenol with zinc dust. Zinc dust will convert the phenol with benzene and zinc oxide. Oxidation of phenol Na2CO3 or Na2Cr2O7 H2SO4, it will be converted into benzoquinone. Some commonly important alcohol such as methanol. Methanol is produced by catalytic dehydrogenation of the carbon monoxide at high pressure and temperature in presence of zinc oxide Cr2O3 catalyst. So carbon monoxide and hydrogen will be converted into methanol. This is called syngas. Methanol is a colorless liquid, boils at 337 K. It is highly poisonous in nature. Ingestion of very small quantities of methanol can cause blindness, and large quantities cause even death. Methanol is used as a solvent in plants and varnishes, chiefly for making formaldehyde. Ethanol is obtained commercially by fermentation of the oldest method. If we take sucrose and give the invertase enzyme, so it will be converted into glucose and fructose. Then if we give zymase enzyme, then zymase enzyme will convert the glucose or fructose into ethanol and CO2. Preparation of ether by dehydration of alcohol. Here the temperature is important. If ethyl alcohol is treated with concentrated sulfuric acid in presence of 443 Kelvin temperature, it will be converted into ethylene gas or alkene product, and the temperature is lower, if it is controlled as 413 Kelvin, then it will be converted into ether by dehydration of one molecule of water. Here is the reaction mechanism given. Now come to important reaction, Williamson synthesis. This is an important laboratory method. Here we use the alkyl halide and an alkoxide ion to form a ether. So alkyl halide will be primary alkyl halide and alkoxide ion will be secondary alkoxide ion. So it will be ROR. So the reaction will be in SN2 mode. So this ether will be formed. If we take this tertiary alkyl bromide and this methoxide ion, then it will give alkene as a product. Then it will give alkene as a product by E2 elimination. By E2 elimination reaction. By E2 elimination reaction. Physical properties. Boiling point of ether is slightly greater than that of simple alkane. Here the boiling point is due to the dipole-dipole interaction. Here CO bond in ether is polar, thus there will be only dipole-dipole interaction, and for here N-pentane is given, here will be on with van der Waals forces. So the boiling point of ether will be higher than that of alkane. The large difference in the boiling point of alcohol and ether is due to the presence of hydrogen bonding in alcohols and not present in ether. Miscibility of ether with water resembles those alcohols are same molecular masses. So it can form intermolecular hydrogen bonding with water molecules. Chemical reaction. Cleavage of CO bond in ether. ROR. The ether while react with the HX, it will cleave the bond into Rx and ROH. Now the problem is which one will be Rx, which one will be ROH. It will depend upon the formation of the oxonium ion, the stability of the oxonium ion, or SN2 attack of the halide ion. The order of the reactivity of the hydrogen halide as follows: HI is greater than HBr greater than HCl. The cleavage of the ether takes place with the concentrated HI or HBr at high temperature. First it will be protonated. This is the protonated ether, and iodine next will attack through SN2 process. It will prefer to attack the CH3 part rather than this CH2 CH3 part, more bulky part. So it will attack, iodide will attack the less bulky part. So the product will be methyl iodide and CH3 CH2OH. So this protonation process is slow. And the cleavage of the ether, at first this form, and iodine will attack here. This is fast. The formation of carbocation is important for cleavage of ethers. Electrophilic substitution reaction. If we take anisole or alkyl phenol, alkoxy group, so it is actually para-directing group. So here bromination will occur in para position as a major product, and in ortho position it will be minor product. Next come to Friedel-Crafts alkylation reaction. This will be major product. Next come to Friedel-Crafts acylation reaction. Here the catalyst is anhydrous AlCl3, and for alkylation it is taken alkyl halide, and for acylation it will be acyl chloride. Nitration will take the mixed acid. Mixed acid is mixture of HNO3 and H2SO4. It will give para-nitroanisole and orthonitroanisole. Para-nitroanisole or 4-nitroanisole will be the major product. Okay, thank you. This is the end of this chapter.